Hello everyone, my name is Dominik Niemietz. I'm a scientist in the group of Gerhard Rempe at the Max-Planck-Institute of Quantum Optics, which is one of the institutes that form MCQST. Today I want to show you a lab where we are working with crossed optical fiber cavities in which we trap a single atom. This is a 360 degrees video, and if you choose your finger or your mouse and you click into the video, you can steer the camera view. So for instance, if you move the video horizontally, you should see our camera operator Chris. Or if you swipe down, you should see the bottom. Okay, having said this, we can go to the MPQ, and due to the corona situation, we are wearing masks. So let's go. Okay, we are now in the so-called Cavity X lab. This lab divides into two parts. The first is an optical table on which we have installed a vacuum chamber, which includes the crossed optical fiber cavities, the mechanics and optics which is needed in order to trap a single atom in the crossed cavities. A second part is, again, an optical table on which we have installed the coherent light sources, which are in our case external cavity diode lasers, which are the blue devices that you can see. Moreover, we prepare the properties of the light, such as the polarization, the frequency, the pulse duration, or the optical power. For instance, we have to control the frequency of the laser by superimposing the light of the laser with the light of a frequency comp. And this light is sent to a conventional photodetector where we detect the beat signal, from which we infer an error signal and a control signal which we feed back to the laser. Another part are AOM tracks, which occur in a highly repetitive way. So we use an AOM in order to fine-tune the frequency, the optical power, or the pulse duration. And after the laser has passed this AOM track, we couple the light into a polarization maintaining fiber, which guides the light from the laser table to the cavity table. But before I come to the cavity table, I first want to show you some images that should illustrate how our experiment works and looks. So in this figure here, you have a close-up of the crossed optical fiber cavities. So we have two cavities which form the short cavity. We have two fibers which form the short cavity with a length of 80 micrometer. And we have two fibers which form the long cavity with a length of 162 micrometer, where the length is limited due to the diameter of the used fiber for the short cavity. And in the crossing point of both cavities, we place a single atom, which is here indicated with this white dot. Meanwhile, we have installed an imaging system which is collecting the fluorescence light of the atom and then is imaged onto a highly sensitive EMCCD camera. And with that, we can take images that look like this. So this is an image of a single trapped atom. So you might wonder, how do we bring a single atom into the crossing point? And this is shown here. So again, we have you see here two fibers which are clamped in these white colored structures, and all four fibers are aligned in horizontal plane in the lab frame. And above the cavity plane, we have two in-vacuum mirrors here colored in pink. And these mirrors are used to reflect the laser beams of the magneto-optical trap colored here in yellow. There is another beam which you cannot see right now, which is sticking out of the plane. And the point where all the beams cross, this is the location of our magneto-optical trap, which takes 2 seconds. And during that time, we accumulate thousands of atoms. After this 2 seconds, we turn the mod off and the atoms fall down due to gravity towards the cavity plane. And the density and the location of the mod is adjusted such that there is a mean one atom that is passing the crossing point, and with a cooling beam and 3 standing wave optical dipole traps, we can trap this atom for tens of seconds. So I want to show you an image of the interior of our vacuum chamber. which has a perspective as indicated here with this eye. So we look from the top to the bottom, so towards the cavity plane. This is what you can see here. So here are the two mod mirrors. Here are the cross cavities in the center. The fibers are clamped in Marquardt structures, which in turn is glued to a piezo with which we control the length of the cavities. And we also have in-vacuum microwave antennas with which we generate microwave fields so that we can coherently manipulate the atomic spin state. Okay, having said this, let's have a look onto the cavity table. So, for instance, here you see one of the 4 optical fibers which is put into an aluminum structure in order to protect the fiber from its environment. This fiber is guided towards the vacuum chamber where we couple the light into the chamber via a fiber feed-through. We have also here a current coil, and we have an exact copy of this coil on the other side of the table. And these two coils, they create a magnetic gradient field that is needed for the magneto-optical trap. If you now look through this hole here in the breadboard, you should get an impression how the interior looks like. So you see a lens, which is a lens that collects the atomic fluorescence light, for instance. And above that lens, you can maybe see white-colored structures, which are the elements with which we clamp our optical fibers. Okay, so you might wonder, what are you doing with such a system, having a single atom that is coupling to 2 independent cavity modes? And this is what I want to talk about now. So for instance, you can have one cavity mode that is tuned to this transition and another one which is tuned to this transition, and you can have an external classical field in order to create such an N-type scheme. You could also choose the levels, the transitions and the cavity resonances such that you can create a 4-wave mixing scheme, or a lambda scheme, or a ladder scheme. As a last point, I want to present you an experiment that we have done shortly after we have successfully installed the system, which is a heralded and passive quantum memory. Here we store a photonic qubit into the spin states of an atom. So how do we do this? We have a single atom again in the cross cavities, and we prepare the atom in a certain spin state. Then we tune the long cavity, so the red colored cavity, or in this context also called qubit cavity, to this transition. And we tune the short cavity, in this context called the herald cavity, to this transition. Then we take a qubit photon, which encodes its information in the polarization degree of freedom, and we send it onto the long cavity. And when the photon reaches the atom cavity system, then the atom will undergo this transition. So it starts here, and it will end up in the storage states. So depending on the polarization of the qubit photon, the atom either goes this way, or if it's in a superposition, it goes both ways. So the atom states are also in a superposition. There are 2 things which are nice about this quantum memory. The first is that at the storage process, we simultaneously emit a pi-polarized photon into the short cavity, no matter what the qubit state is. We can detect this photon, and this detection tells us that the storage has succeeded or not. The second thing is that this transition is enabled by the presence by the cavity. So we stimulate the transmission of the photon into the cavities by this herald cavity. Otherwise, if you wouldn't have this cavity, you might choose an external field like a stirrup, which requires the control of many properties which might be technologically challenging. Okay, having said this, let's talk about the readout. How do we do this? And this is actually the reverse process of the write-in. So we take a pi-polarized photon, and we send it onto the short cavity. And the atom, which is now in its storage states, will do the reverse process. So it starts here and it will end up in the initial state by simultaneous emission of the original qubit photon, which is emitted into the long cavity. So if you want to know more about this work, I refer you to this publication, where we provide many more details and numbers and also details about the crossed optical fiber cavity system. So this was it from my side. I hope you enjoyed the tour. Stay healthy and goodbye.